I'm Brian Goldblatt, and this is the Mass of a Black Hole Lab.
The goal of this lab was to calculate the mass of the black hole based on the mass of a star and a simulated trajectory of motion. We made some assumptions in this lab, mainly being that the black hole is at the origin, the star has a mass of 2e30 kilograms, the net force on the star is due solely to the black hole at the origin, and the time between data points is exactly 1 day, being 86,400 seconds. Some relevant principles that we used to do the math in this lab were Newton's second law, the momentum principle, and Newton's universal law of gravitation. So, dp/dt, the momentum principle. dp/dt is the change in momentum over time and is defined as f net. Since dp/dt is a vector, it can be written as d dt of the absolute value of p times p hat, and it can be separated into its components of d absolute value p over dt times p hat plus absolute value p times dp hat dt. Now, it is clear to see that these separated components of dp/dt make up the parallel and perpendicular forces of F net. So, we can say that F net parallel is d absolute value of p dt times p hat, and F net perpendicular is absolute value of p times dp hat dt. Only the parallel component can change the magnitude of the momentum, and only the perpendicular component can change the direction of the momentum. The gravity law. Since the absolute value of F net is the absolute value of dp/dt, and the only force applied in this lab is gravity, therefore the absolute value of F net is the absolute value of the force of gravity. And that can be defined as big G m1 times m2 over the absolute value of the distance. Well, it's just the distance squared. So the mass of the black hole can be found when rearranged to be equal to absolute value of dp/dt times absolute value of position squared over gravity times m1. Here's my simulation being played in GlowScript. The pink arrow is the parallel force, the blue arrow is the perpendicular force, and the orange arrow is the total F net. The constants that I used in my simulation code were gravity, big G, being 6.7 e to the negative 11, the mass of the star being 2e30 kilograms, and the delta t being 86,400 seconds, or 1 day, and the start time was 0 seconds. Here's the momentum principle in the simulation code. As you can see, I'm finding the initial and final velocities and momentums. dp/dt is the change in momentum over the change in time, and I set that equal to F net, and I calculated p hat to help find both the parallel and perpendicular components of the F net force. And I simulated the mass of the black hole using Rmag being the magnitude of the star position vector, and the mass of the black hole being magnitude of F net times Rmag squared over big G times the mass of the star. And that corresponds to the equation that I had shown earlier on this slide. So the results of my simulation showed that the average mass of the black hole based on my email address was 9.2 e to the 33 kilograms. The minimum mass was found to be 8.94 E33 kilograms, and the maximum was 9.51 E33 kilograms. And this is a graph showing the F net distribution over time, where the blue line is the magnitude of F net, the orange line is the magnitude of the perpendicular component of F net, and the gray line is the magnitude of the parallel component of F net. As you can see, the parallel component is very jittery, and a potential source of this error was just maybe that the computational software may need to be upgraded in order to do the calculations more properly. So what does it mean? Mathematically, F net and dp/dt are exactly the same thing. As it was defined earlier, F net parallel is d absolute value of p dt times p hat, and F net perpendicular is absolute value of p dp hat dt. However, there is a difference in calculating these two quantities. A change in momentum can be observed and quantified by the eye as a result of changing velocity and position over time. Fnet, however, is much harder to obtain and is something that is impossible to calculate in this simulation without knowing the mass of the black hole first, which was the quantity that we were trying to identify to begin with. So what if the black hole were replaced by a new black hole, but the motion of the observed star remained unchanged? Well, nothing would really change about the mass of the black hole. The mass was found using the changing position over time from the star, so if that were to remain unchanged, then the mass of the new black hole will remain the same as the original one that I've calculated in this lab.